The sharpness of the signal also influenced how it interacted with noise reduction techniques. Averaging, filtering, and smoothing processes that typically suppress noise did not erase the signal. Instead, its edges remained visible, reinforcing the impression that it was not a statistical fluctuation. Noise tends to lose definition when subjected to such processing. Structured signals retain it. These features prompted analysts to consider models that could generate such precision. They examined whether certain plasma instabilities, resonance effects, or geometric alignments could produce emissions with narrow frequency ranges and abrupt transitions. While some scenarios could approximate parts of the behavior, none provided a complete and comfortable fit without invoking uncommon or finely tuned conditions. What made this especially compelling was the consistency across observations. The signal did not occasionally appear sharp and narrow, it did so reliably. That reliability suggested that the observed characteristics were intrinsic to the source rather than artifacts of observation. Each repetition reinforced the conclusion that the signal's clean profile was not accidental. In the broader context of radio astronomy, narrow bandwidth and sharp edges function like signatures. They do not identify a source outright, but they eliminate large categories of possibilities. By narrowing the field of explanation, these traits transformed the signal from an ambiguous curiosity into a well-defined anomaly, one whose precision demanded a level of explanation beyond what random noise or typical astrophysical processes usually provide. As analysis progressed, one of the most important steps was comparing the signal's behavior against known classes of astrophysical radio sources. Pulsars and fast radio bursts are among the most studied and well-documented phenomena in this domain, and they often serve as the first points of reference when unusual signals appear. If the signal matched either of these categories, it would provide a familiar and physically grounded explanation. However, careful comparison revealed significant mismatches that made such identifications increasingly unlikely. Pulsars are rapidly rotating neutron stars that emit beams of radiation sweeping across space like lighthouse beams. Their signals are highly periodic, often repeating with extraordinary regularity over timescales ranging from milliseconds to seconds. Importantly, pulsar emissions typically show a characteristic frequency dependence. Their pulses often broaden and smear at lower frequencies due to interactions with the interstellar medium, and their spectra tend to span wide frequency ranges. The signal under analysis did not display this kind of frequency-dependent behavior. Its narrow bandwidth and sharp edges were inconsistent with the complex, multi-frequency profiles commonly observed in pulsars. Timing also posed a problem. Pulsar periods are exceptionally stable and can often be predicted with extreme precision. While the signal showed repetition, its timing did not align with the rigid periodicity expected from a rotating neutron star. There was no evidence of the gradual spin down that pulsars exhibit over time, nor were there harmonics or sub-pulses that usually accompany pulsar emissions. These absences made it difficult to reconcile the signal with even an unusual or previously unknown pulsar. Fast radio bursts presented another possible comparison. These are brief, intense flashes of radio energy originating from distant galaxies, often lasting only milliseconds. Some repeat, while others appear to be one-time events. However, fast radio bursts are typically broadband, spreading across a wide range of frequencies. They also exhibit dispersion signatures, frequency-dependent delays caused by their passage through interstellar and intergalactic plasma. The signal in question lacked these dispersion characteristics. Its arrivals were not staggered across frequencies in the way fast radio bursts are, and its energy was confined rather than spread. Additionally, fast radio bursts are usually extremely energetic, often standing out dramatically against background noise. The signal under analysis was comparatively subtle. It did not dominate the data or overwhelm the detectors. Instead, it sat quietly above the noise floor, detectable only through careful processing. This difference in intensity further weakened the case for an FRB like origin. Beyond pulsars and fast radio bursts, other known sources were also considered. Stellar flares, planetary radio emissions, and magnetospheric interactions can all produce radio signals, but these tend to be irregular, broadband, or strongly influenced by environmental conditions. None of these categories naturally produce the combination of repetition, narrow bandwidth, and sharp temporal boundaries observed here. Ruling out these explanations was not a single decisive step, but a gradual process. Each comparison eliminated some possibilities while raising new questions. Importantly, elimination does not equate to proof of something exotic. It simply means that the signal does not fit comfortably within existing frameworks. Science advances not by declaring mysteries, but by identifying where current models fall short. This mismatch with known phenomena is what gave the signal its status as an anomaly. An anomaly is not evidence of new physics or unfamiliar sources. It is a sign that the observation sits at the edge of understanding. It signals the need for either refined models or the recognition of rare conditions that have not been extensively documented. By systematically testing and discarding familiar explanations, researchers strengthened the case that the signal deserved continued attention. It was not enough to note that the signal was unusual, it had to be unusual in specific, well-defined ways. The failure of standard categories to account for its behavior did not provide answers, but it sharpened the questions that would guide future investigation. Before any serious interpretation could take place, it was essential to determine whether the signal originated from Earth rather than from space. Terrestrial interference is one of the most common and deceptive challenges in radio astronomy. Modern society fills the radio spectrum with transmissions from satellites, aircraft, communication networks, radar systems, and countless electronic devices. Many of these signals can appear unexpectedly in astronomical data, sometimes mimicking patterns that seem unusual or intriguing until their true source is identified. The first step in ruling out Earth-based interference was to examine the signal's relationship to known satellite activity. Satellites follow predictable orbits, and their transmissions often recur at regular intervals tied to those paths. When a satellite passes through a telescope's field of view, it typically produces a signal that drifts in frequency due to relative motion, leaving a characteristic trace. The signal under analysis did not exhibit this drifting behavior. Its frequency remained stable, and its timing did not correspond to known satellite pass schedules. Geographic considerations were also important. Terrestrial interference often appears simultaneously across multiple frequencies or affects multiple observations taken at the same time. In contrast, this signal was confined to a specific frequency range and did not contaminate adjacent bands. This localization reduced the likelihood that it was caused by broad-spectrum interference, such as radar or communication bursts, which usually leave wider spectral footprints. Another key test involved comparing observations from different times and conditions. Human-made interference is often linked to local activity, power usage cycles, nearby equipment, or specific operational windows. If the signal were terrestrial, its appearance would likely correlate with such factors. Instead, the signal emerged under varying observational conditions, without clear alignment to local time, weather, or known operational schedules. This inconsistency weakened the case for a ground-based source. Instrumental artifacts were also carefully considered. Complex data processing pipelines can sometimes introduce artificial patterns, especially when filtering or averaging techniques are applied. To guard against this, analysts examined raw, unprocessed data to confirm that the signal was present before any transformations were applied. Independent processing methods were used to ensure that the pattern did not arise from a specific algorithm or calibration error. The persistence of the signal across these checks supported the conclusion that it was not a processing artifact. Cross-referencing with known databases of interference further narrowed the possibilities. Many observatories maintain detailed records of recurring sources of radio contamination, including specific frequencies and signatures associated with common transmitters. The signal did not match any entries in these catalogs. Its profile lacked the modulation patterns, harmonics, and sidebands that typically reveal human-made transmissions, even when those transmissions are weak or partially obscured. Another telling factor was directionality. Terrestrial interference often enters a telescope's detectors from multiple directions or through side lobes rather than the main observing beam. This can cause such signals to appear inconsistently as the telescope moves. The signal under study behaved as though it were coming from a fixed direction in the sky, maintaining its characteristics as the telescope tracked its target. This spatial consistency is difficult to reconcile with local interference sources. The process of elimination was deliberately conservative. Analysts assumed a terrestrial origin until evidence suggested otherwise. Each test did not prove the signal was extraterrestrial, but collectively they made a local explanation increasingly implausible. By the time these checks were complete, the probability that the signal resulted from satellite interference, ground-based transmissions, or instrumental effects had been significantly reduced. This careful exclusion of mundane explanations was a critical step. Only by exhausting the most ordinary possibilities could the signal be treated as a genuine astronomical observation. The absence of a clear terrestrial cause did not elevate the signal to something extraordinary, but it did justify continued investigation with the confidence that what was being studied was not merely an echo of our own technology. Understanding the distinction between a ping and a message is essential to interpreting the signal responsibly. A message implies complexity. It carries information encoded in patterns that can be decoded, translated, and interpreted. Language, symbols, modulation schemes, or structured data streams are all hallmarks of a message. A ping, by contrast, is simple. It is a single act, repeated or isolated, whose primary function is detection rather than communication. In many technological systems, pings are used to confirm presence or establish contact without exchanging information. Sonar pings reveal objects by reflection. Network pings verify that a system exists and can respond. Radar pings announce a mission and await a return signal. In all of these cases, the ping itself is not the content, it is the precursor to content. It answers the question, something there? Rather than what is being said. This analogy matters because it frames expectations. When the signal is described as ping-like, it explicitly rejects the idea that it contains encoded meaning. There are no complex modulations, no nested patterns, no frequency shifts carrying bits of data. The signal does not evolve into a sequence that suggests syntax or structure beyond its own repetition. Its simplicity is its defining feature. From a scientific standpoint, this simplicity is reassuring rather than alarming. Claims of messages require extraordinary evidence because they imply intention, design, and purpose. A ping does not. It can arise from natural processes just as easily as from technological ones. Many physical systems produce discrete pulses without encoding information. Lightning strikes, magnetospheric interactions, and certain plasma instabilities all generate brief, repeated emissions that resemble pings in form. By emphasizing that the signal functions as an announcement rather than a statement, researchers maintain a cautious interpretive stance. The language used avoids assigning meaning where none can be demonstrated. This is critical for maintaining scientific credibility, especially in areas where public imagination can easily outrun evidence. The distinction also guides analysis. Searching for a message would involve looking for modulation patterns, information density, error correction, or compression, features that simply are not present here. Instead, analysis focuses on timing, frequency stability, and physical plausibility. The questions become about mechanism rather than meaning. What process could produce this pulse, under what conditions, and with what energy source? This framing helps prevent cognitive bias. Humans are pattern, seeking by nature, and there is a strong temptation to interpret any structured signal as intentional. By clearly defining the signal as a ping, analysts resist that temptation. They acknowledge structure without assigning agency. This keeps the investigation grounded in testable hypotheses rather than speculative narratives. Importantly, a ping does not need an audience. A message presupposes a receiver capable of interpretation. A ping does not. It can exist entirely independent of observation, simply as a consequence of physical processes repeating in time. This neutrality is one of the reasons the term is useful. It describes behavior without implying purpose. In broader scientific practice, many discoveries begin with ping-like observations. A transient signal alerts researchers to the existence of a phenomenon long before its nature is understood. Only later, after extensive study, does context and explanation emerge. In this sense, the signal's role is not to inform, but to prompt investigation. By maintaining the distinction between ping and message, researchers protect the integrity of the inquiry. They leave open the full range of explanations while clearly ruling out the most sensational interpretations. The signal stands as a marker of something happening, not a declaration of what that something means. A central theme in the analysis of this signal is the deliberate choice to prioritize curiosity over belief. Curiosity drives investigation. Belief seeks conclusion. In science, confusing the two can derail understanding. From the earliest stages of examining the data, researchers resisted the temptation to interpret the signal as evidence of anything beyond what could be directly observed. Instead of asking what the signal meant, they asked how it behaved. This shift in focus is subtle but crucial. Belief often enters analysis when observations are framed as answers rather than questions. In this case, the data offered no answers, only irregularities. Treating those irregularities as proof of a particular explanation would have closed off alternative possibilities prematurely. Curiosity, by contrast, keeps the inquiry open. It allows researchers to explore multiple hypotheses without becoming attached to any single one. This mindset is especially important in fields where ambiguity is unavoidable. Radio astronomy deals with incomplete information filtered through distance, noise, and instrumentation. Many signals cannot be reproduced on demand or examined directly. Under these conditions, belief becomes a liability. It encourages selective interpretation, where data that fit a preferred narrative are emphasized while conflicting evidence is minimized or ignored. By emphasizing curiosity, analysts adopt a posture of humility. They acknowledge the limits of current knowledge and accept uncertainty as part of the process. This does not weaken the investigation, it strengthens it. When uncertainty is openly recognized, methods become more rigorous, checks become more thorough, and conclusions become more reliable. The language used in describing the signal reflects this philosophy. Words are chosen carefully to describe observable properties without implying cause or intent. Terms like anomaly, pattern, or ping-like are descriptive, not explanatory. They communicate what is seen without claiming to know why it is seen. This precision in language acts as a safeguard against overinterpretation. Curiosity also shapes how results are communicated. Rather than presenting the signal as a breakthrough or revelation, it is framed as an invitation to further study. This approach encourages independent verification and alternative interpretations. It recognizes that no single analysis is definitive, and that understanding emerges through collective effort over time. Historically, many scientific missteps have occurred when belief outpaced evidence. Signals once thought to indicate intelligent origins were later explained by natural phenomena. Each of these episodes reinforced the importance of restraint. They taught scientists to slow down, to question their assumptions, and to demand rigorous proof before embracing extraordinary explanations. In this context, curiosity acts as a stabilizing force. It keeps the investigation anchored to data rather than speculation. It encourages patience, allowing patterns to reveal themselves gradually rather than being forced into preconceived frameworks. This patience is particularly important when dealing with rare or subtle phenomena, where small errors in interpretation can have large consequences. The emphasis on curiosity also acknowledges the emotional dimension of discovery. Unusual signals naturally provoke excitement, wonder, and imagination. Rather than suppressing these responses, science channels them productively. Curiosity transforms emotional reaction into systematic inquiry. Belief, if unchecked, can transform it into premature certainty. Ultimately, choosing curiosity over belief preserves the integrity of the scientific process. It ensures that conclusions, when they finally emerge, are grounded in evidence rather than desire. In the case of this signal, that choice keeps the door open to multiple explanations while protecting against the allure of definitive but unsupported claims. A central theme in the analysis of this signal is the deliberate choice to prioritize curiosity over belief. Curiosity drives investigation, belief seeks conclusion. In science, confusing the two can derail understanding. From the earliest stages of examining the data, researchers resisted the temptation to interpret the signal as evidence of anything beyond what could be directly observed. Instead of asking what the signal meant, they asked how it behaved. This shift in focus is subtle but crucial. Belief often enters analysis when observations are framed as answers rather than questions. In this case, the data offered no answers, only irregularities. Treating those irregularities as proof of a particular explanation would have closed off alternative possibilities prematurely. Curiosity, by contrast, keeps the inquiry open. It allows researchers to explore multiple hypotheses without becoming attached to any single one. This mindset is especially important in fields where ambiguity is unavoidable. Radio astronomy deals with incomplete information filtered through distance, noise, and instrumentation. Many signals cannot be reproduced on demand or examined directly. Under these conditions, belief becomes a liability. It encourages selective interpretation, where data that fit a preferred narrative are emphasized while conflicting evidence is minimized or ignored. By emphasizing curiosity, analysts adopt a posture of humility. They acknowledge the limits of current knowledge and accept uncertainty as part of the process. This does not weaken the investigation, it strengthens it. When uncertainty is openly recognized, methods become more rigorous, checks become more thorough, and conclusions become more reliable. The language used in describing the signal reflects this philosophy. Words are chosen carefully to describe observable properties without implying cause or intent. Terms like anomaly, pattern, or ping-like are descriptive, not explanatory. They communicate what is seen without claiming to know why it is seen. This precision in language acts as a safeguard against overinterpretation. Curiosity also shapes how results are communicated. Rather than presenting the signal as a breakthrough or revelation, it is framed as an invitation to further study. This approach encourages independent verification and alternative interpretations. It recognizes that no single analysis is definitive, and that understanding emerges through collective effort over time. Historically, many scientific missteps have occurred when belief outpaced evidence. Signals once thought to indicate intelligent origins were later explained by natural phenomena. Each of these episodes reinforced the importance of restraint. They taught scientists to slow down, to question their assumptions, and to demand rigorous proof before embracing extraordinary explanations. In this context, curiosity acts as a stabilizing force. It keeps the investigation anchored to data rather than speculation. It encourages patience, allowing patterns to reveal themselves gradually rather than being forced into preconceived frameworks. This patience is particularly important when dealing with rare or subtle phenomena, where small errors in interpretation can have large consequences. The emphasis on curiosity also acknowledges the emotional dimension of discovery. Unusual signals naturally provoke excitement, wonder, and imagination. Rather than suppressing these responses, science channels them productively. Curiosity transforms emotional reaction into systematic inquiry. Belief, if unchecked, can transform it into premature certainty. Ultimately, choosing curiosity over belief preserves the integrity of the scientific process. It ensures that conclusions, when they finally emerge, are grounded in evidence rather than desire. In the case of this signal, that choice keeps the door open to multiple explanations while protecting against the allure of definitive but unsupported claims. Scientific progress often begins not with answers, but with discomfort. Anomalies are observations that do not fit comfortably within existing models, and history shows that these moments of mismatch are where understanding tends to advance. Rather than being inconveniences, anomalies act as signals themselves, pointing to gaps in knowledge or limitations in current theories. They force scientists to re-examine assumptions that may have gone unchallenged for years or even decades. In many cases, anomalies initially appear insignificant. They may be dismissed as measurement errors, statistical flukes, or artifacts of instrumentation. This skepticism is healthy and necessary. Most anomalies do disappear under closer scrutiny. But when one persists, when repeated observations continue to resist explanation, it begins to exert pressure on established frameworks. That pressure can lead to refinement, revision, or, in rare cases, transformation of scientific understanding. The history of astronomy is filled with such examples. The irregular motion of Uranus led to the prediction and discovery of Neptune. The unexpected behavior of Mercury's orbit exposed the limits of Newtonian gravity and helped pave the way for general relativity. The discovery of cosmic background radiation emerged from what was initially considered experimental noise. In each case, an anomaly was not a failure of observation, but a clue that something deeper was at work. What makes anomalies powerful is not their strangeness, but their persistence. A single unexplained event carries little weight. A pattern of unexplained behavior, documented carefully and reproduced independently, becomes impossible to ignore. It demands attention not because it is dramatic, but because it refuses to conform. This refusal is what transforms an observation into a problem worth solving. Anomalies also play a crucial role in sharpening scientific tools. When existing models fail, scientists are compelled to improve their measurements, develop more sensitive instruments, and refine analytical techniques. Even if the anomaly eventually finds a conventional explanation, the process of chasing it often leads to broader advancements. In this way, anomalies contribute to progress regardless of their ultimate resolution. Importantly, the presence of an anomaly does not imply that current theories are wrong in a general sense. More often, it indicates that those theories are incomplete or applied outside their optimal range. Science rarely advances by discarding entire frameworks overnight. Instead, it evolves by extending, modifying, or contextualizing them. Anomalies provide the motivation for this evolution. The careful handling of anomalies requires balance. Too much skepticism can cause genuine discoveries to be overlooked. Too little can lead to premature conclusions. The scientific method navigates this tension by demanding rigorous evidence while remaining open to revision. Anomalies sit at the center of this balance, challenging scientists to maintain both discipline and imagination. In the context of signal analysis, an anomaly does not announce its significance. It simply exists, quietly defying easy classification. Its value lies in what it prompts researchers to ask. Why does this behave differently? Under what conditions could known processes produce such an effect? Are there missing variables or overlooked interactions? Each question expands the scope of inquiry. Ultimately, anomalies remind us that knowledge is provisional. They expose the edges of understanding and invite exploration beyond them. Even when they do not lead to revolutionary discoveries, they refine the boundaries of what is known. In doing so, they uphold the dynamic nature of science, a process driven not by certainty, but by the continual encounter with the unexpected. At its deepest level, the signal serves as a reminder of why humanity listens to the universe in the first place. Long before advanced instruments and complex data analysis existed, people looked up at the sky driven by curiosity rather than certainty. Modern science has refined that curiosity into systematic observation, but the underlying impulse remains the same. We listen not because we expect clear answers, but because the act of listening expands our understanding of where we exist within a vast and dynamic cosmos. Most of the time, the universe offers no direct response. Telescopes record background radiation, random fluctuations, and familiar patterns that confirm what is already known. This silence is not emptiness. It is the natural state of a universe governed by processes that operate on scales far removed from human experience. Yet within that apparent silence, scientists continue to search, motivated by the knowledge that discovery often emerges from patience rather than expectation. When a signal resists immediate classification, it briefly disrupts that silence. It does not explain itself, and it does not announce significance. Instead, it prompts reflection. It forces observers to slow down and consider the possibility that their current models, while effective, may not capture every nuance of reality. In this way, the signal becomes less about its own origin and more about the perspective it offers on the limits of understanding. Listening to the universe is not an act of passive reception, it is an active process of interpretation. Instruments must be designed, data must be filtered, and assumptions must be questioned. Each of these steps reflects a deliberate choice to engage with the unknown rather than retreat into certainty. Signals that challenge expectations reaffirm the value of this engagement. They validate the effort invested in careful observation, even when definitive answers remain elusive. There is also a philosophical dimension to this process. By listening, humanity acknowledges that it is not the center of the universe, but a participant within it. Signals arriving from distant regions of space remind us that reality extends far beyond the boundaries of daily life. They connect the human scale to the cosmic scale, linking momentary observations to processes unfolding over millions or billions of years. Importantly, the motivation to listen is not driven by the promise of discovery alone. It is driven by the recognition that understanding the universe is inseparable from understanding ourselves. Each refinement in knowledge reshapes our sense of place, our appreciation of complexity, and our respect for the limits of certainty. Even ambiguous signals contribute to this process by highlighting how much remains unknown. The signal's greatest contribution may therefore be symbolic rather than explanatory. It exemplifies the moment when randomness gives way to question, when noise becomes something worth examining more closely. Such moments reaffirm the purpose of scientific inquiry. They demonstrate that exploration is not only about accumulating facts, but about cultivating a mindset willing to confront uncertainty with patience and rigor. In the end, listening to the universe is an expression of humility. It accepts that answers may be partial, delayed, or absent altogether. Yet it persists, guided by the understanding that progress does not require constant revelation. Sometimes, it is enough for a signal to remind us that the universe is still capable of surprising us, and that the simple act of listening remains one of humanity's most powerful tools for discovery. The analogy to a ping arises directly from this behavior. In many technological contexts, a ping is a brief, discrete emission repeated at controlled intervals. It is not continuous, and it does not carry complex information. Its purpose is simply to register presence or establish contact. While no claim is made that the signal serves such a purpose, the comparison helps convey the difference between this pattern and the continuous or chaotic emissions more commonly observed in space. From a statistical standpoint, the repetition reduced the likelihood that the signal was a random fluctuation. Each recurrence added weight to the observation, making coincidence increasingly improbable. Analysts are trained to be cautious with small datasets, but even conservative thresholds begin to shift when a pattern persists across multiple independent observations. Repetition turns an isolated curiosity into a phenomenon that demands modeling. This behavior also influenced how the data were processed. Instead of treating each detection as an independent event, analysts began to examine correlations between them. They looked for subtle changes in timing, strength, and frequency that might reveal an underlying mechanism. This comparative approach transformed the signal from a single anomaly into a sequence with internal relationships, opening new avenues for interpretation. Importantly, the precise repetition did not eliminate uncertainty, it refined it. The question was no longer whether something unusual had been detected, but what kind of process could produce such behavior. Natural explanations were still favored, but the range of plausible candidates narrowed. The repetition acted as a filter, separating the signal from the vast background of randomness and placing it into a smaller, more intriguing category. In this way, timing became the signal's most informative feature. It spoke not through volume or complexity, but through regularity. Against a backdrop of cosmic noise that rarely repeats itself with intention, like precision, this measured recurrence stood out as a defining characteristic, guiding the direction of further inquiry. As the pattern of repetition became clearer, the language used to describe the signal began to shift. It no longer made sense to think of it as static or interference, because those terms imply randomness and disorder. Instead, the signal evoked something more deliberate in its structure, leading to the comparison with a ping. This word is not a scientific classification, but it captures an important distinction in behavior. A ping is brief, discrete, and intentional in form, even if its origin remains unknown. Static is continuous and messy. It fills space without regard for timing or symmetry. When noise appears in data, it rarely looks the same twice. Its peaks and valleys vary in shape and spacing, and any apparent order dissolves under closer inspection. The signal in question behaved differently. Each appearance was short-lived, sharply defined, and separated by silence. This on-off nature is one of the defining traits that separates a ping-like event from background noise. The clarity of the signal's boundaries reinforced this impression. Noise tends to fade in and out, blending into its surroundings. Here, the signal rose quickly above the background and then dropped away just as decisively. This gave it a pulse-like quality, as though a switch had been momentarily flipped and then turned off again. Such behavior is uncommon in natural radio emissions, which are usually shaped by gradual physical processes rather than abrupt transitions. Another aspect that contributed to the ping analogy was consistency. Each pulse resembled the previous ones closely enough to suggest a common origin. While minor variations were present, the overall shape and duration remained similar. Noise rarely offers this level of repeatability. Even when random processes produce spikes, those spikes tend to differ significantly from one another. Here, the resemblance across events hinted at a controlled or at least stable mechanism. Importantly, calling the signal a ping does not imply communication. A ping contains no embedded information, no modulation carrying data, no complexity that would suggest language or encoding. It is simply a marker in time and frequency, a presence rather than a message. This distinction matters because it frames the interpretation in cautious, observational terms rather than speculative ones. In scientific analysis, metaphors like this serve a practical purpose. They help convey complex behavior in intuitive terms without overcommitting to an explanation. Describing the signal as ping-like immediately tells other researchers what to look for: brevity, repetition, precision, and separation by silence. It shifts attention away from amplitude and toward timing and structure. The comparison also highlights what the signal lacks. There is no continuous carrier wave, no gradual modulation, no spreading across frequencies. Instead, there is simplicity. In a universe where most emissions are the byproduct of large, turbulent systems, simplicity itself becomes noteworthy. It suggests that the source process may be constrained or optimized in some way, even if that constraint arises from natural physics rather than design. This way of framing the signal influenced subsequent investigation. Analysts began testing models that could produce discrete pulses rather than continuous output. They examined whether known natural phenomena could be tuned to behave in this manner under specific conditions. Some candidates were eliminated quickly, others required more detailed simulation. In all cases, the ping-like characterization provided a useful starting point for hypothesis generation. Ultimately, the power of the analogy lies in its restraint. It describes how the signal behaves without claiming to know why it behaves that way. By recognizing that it looks more like a ping than noise, researchers acknowledge an important qualitative difference while leaving the question of origin open. That balance between description and interpretation is essential in maintaining scientific credibility when confronting something unfamiliar. A fundamental way to understand why this signal drew attention is to examine the difference between randomness and structure. Noise, whether cosmic or instrumental, is characterized by the absence of memory. Each fluctuation is independent of the last, shaped by chance interactions and overlapping sources that do not coordinate with one another. If a spike appears at one moment, there is no reason to expect a similar spike to appear again in the same way or at the same interval. This lack of predictability is precisely what defines noise in scientific terms. In radio astronomy, noise manifests as irregular variations in signal strength and frequency that shift continuously over time. Even when noise appears intense, it remains disorganized. Its statistical properties may be well understood, but its specific behavior at any given moment is not repeatable. Analysts can describe the average behavior of noise, but they cannot predict its exact form from one instant to the next. This is why noise is often filtered out through averaging techniques. By combining many observations, the random fluctuations cancel themselves out, revealing any underlying structure. The signal under analysis did not behave this way. Instead of disappearing into the background when averaged or examined over longer timescales, it retained its identity. Its features reappeared with recognizable similarity, indicating that the process producing it was not random. This persistence suggests the presence of memory, a governing mechanism that preserves certain characteristics from one emission to the next. Memory in a signal does not imply intelligence, it implies constraint. Something is limiting how the signal can vary, keeping it within a narrow range of behaviors. In natural systems, such constraints can arise from stable physical conditions, repeating interactions, or resonant processes. What matters is not the cause, but the effect. The signal carries a trace of its past into its future appearances. One clear indication of memory was the consistency of timing. If noise were responsible, the intervals between peaks would scatter widely. Instead, the observed intervals clustered closely, as though the system were referencing an internal clock or cycle. Even when small variations were present, they appeared as deviations from a pattern rather than complete departures from it. This is a hallmark of structured processes. The signal also showed memory in its shape. Each occurrence followed a similar rise and decay profile, suggesting that the same physical conditions were being recreated repeatedly. Noise lacks this capability. It does not recreate shapes, it produces new ones each time. The resemblance between pulses implied a reproducible mechanism, one that resets and repeats rather than evolving unpredictably. This distinction between noise and structure is critical because it changes how scientists engage with the data. Noise is something to be reduced, modeled statistically, and ultimately ignored once characterized. Structure, by contrast, is something to be explained. It invites modeling at the level of physical processes rather than probability distributions. Recognizing structure transforms an observation from background clutter into a candidate for deeper study. Importantly, the presence of structure does not demand an exotic explanation. Many natural phenomena exhibit memory and regularity, from rotating neutron stars to oscillating plasma clouds. However, identifying structure is the first step in narrowing the field of possibilities. It allows researchers to rule out entire classes of explanations that rely on randomness alone. This is why the distinction mattered so much. By demonstrating behavior inconsistent with noise, the signal crossed a threshold of significance. It could no longer be dismissed as a statistical accident or an artifact of random interference. Instead, it occupied a middle ground clearly patterned, yet not immediately identifiable. That middle ground is where scientific progress often occurs, driven by the effort to understand how order can emerge from a universe that is otherwise dominated by chaos. The importance of the hydrogen line at 1420 MHz lies in its universality. Hydrogen is not just another element in the periodic table, it is the fundamental building block of the visible universe. Formed in enormous quantities during the earliest moments after the Big Bang, hydrogen makes up the vast majority of normal matter. Stars are born from it, galaxies are threaded with it, and the space between stellar systems is filled with diffuse clouds of it. Because of this, any observer anywhere in the cosmos, studying the nature of matter, would inevitably encounter hydrogen and its unique spectral signature. The hydrogen line arises from a simple and elegant physical process. Within a neutral hydrogen atom, the proton and electron each have a property known as spin. Most of the time these spins are aligned, but occasionally the electron flips, moving from a higher energy configuration to a slightly lower one. When this happens, a photon is emitted at a wavelength of about 21 centimeters, corresponding to a frequency of 1420 Hz. This transition is governed by fundamental quantum mechanics, meaning it is not dependent on environmental conditions, chemistry, or local astrophysical complexity. It is the same everywhere. Because this emission is rooted in basic physics, it provides a shared reference point across the universe. Unlike visible light, which can be absorbed by dust, or higher energy radiation, which may be blocked or distorted, the hydrogen line travels through interstellar space with relatively little interference. It passes through gas clouds that would obscure other wavelengths, allowing it to act as a long-distance beacon of matter itself. This makes it one of the most reliable tools for observing the large-scale structure of the cosmos. Astronomers have used this frequency to map galaxies far beyond what telescopes can see in visible light. By measuring subtle shifts in the hydrogen line, they can determine how fast galaxies rotate, how much mass they contain, and how they move relative to one another. Entire discoveries, including the evidence for dark matter in galaxies, are tied to observations made at or around this frequency. Over decades of study, scientists have developed an intimate familiarity with how hydrogen line emissions behave under natural conditions. This familiarity is what gives the frequency its diagnostic power. When something appears at 1420 MHz, it can be compared against a deep well of existing knowledge. Analysts know how wide hydrogen emissions should be, how they should drift due to motion, and how they should vary in intensity depending on environment. Any deviation stands out not because it is dramatic, but because it conflicts with expectations shaped by countless prior observations. Beyond its practical utility, the hydrogen line holds conceptual significance. It represents a frequency that does not belong to any one civilization or planet. It is defined by the structure of the atom itself. This universality has long made it a focal point in discussions about cosmic observability. If an observer wanted to choose a frequency that would be recognizable anywhere in the universe, independent of culture or technology, hydrogen would be an obvious candidate. For this reason, the appearance of an unusual signal near this frequency naturally draws attention, not because it implies intention, but because it occurs at a place in the spectrum that is already meaningful. It is like noticing an unexpected mark on a well-known map. The map itself is trusted, that trust makes anomalies harder to ignore. In the context of analysis, the hydrogen line acts as a baseline of order. It represents one of the clearest, most predictable signals the universe provides. When something diverges from that predictability, it invites careful examination. The significance lies not in speculation, but in contrast. A signal appearing near a frequency defined by simplicity and universality invites scrutiny precisely because so much about that frequency is already understood. Over time, certain assumptions have emerged about how signals might be detected across interstellar distances, and simplicity has always been central to those ideas. Long before any specific anomalies were discussed, scientists considered what characteristics a signal would need in order to be noticeable against the immense background of cosmic noise. One conclusion repeatedly surfaced: a signal tied to a fundamental constant or universal property of nature would stand the best chance of being recognized by any advanced observer, regardless of their origin or perspective. The frequency associated with neutral hydrogen naturally fits this criterion. Hydrogen is the most common element in the universe, and its spectral signature is one of the first things any civilization studying astronomy would uncover. Unlike frequencies chosen arbitrarily or based on local technology, the hydrogen line is dictated by quantum mechanics. It exists independently of culture, biology, or environment. That universality makes it an intuitive focal point when thinking about detection across vast cosmic scales. Because of this, the hydrogen line has often been described as a kind of cosmic meeting place, not a location in space, but a shared reference in the electromagnetic spectrum. It is a frequency where natural emissions already occur, but where deviations from expected behavior would be immediately noticeable. This dual role, common enough to be known, yet precise enough to stand out, gives it a unique status in signal analysis. From a practical standpoint, focusing attention on this frequency also makes sense because it is relatively quiet. International agreements have limited human-made transmissions in this band to protect astronomical research. As a result, there is less contamination from terrestrial sources compared to other parts of the radio spectrum. For analysts, this reduces ambiguity. When something appears at or near this frequency, there is a higher likelihood that it originates beyond Earth rather than from local interference. The idea that such a frequency could serve as a logical channel for detection does not depend on assuming intention or communication. Even natural phenomena benefit from being observed in a clean, well-understood band. However, the historical discussion surrounding this frequency has shaped how scientists respond to anomalies within it. Signals detected here are often subjected to especially careful scrutiny, not because they are expected to be extraordinary, but because the context amplifies their significance. This attention is grounded in decades of thought experiments and theoretical work about observability. Scientists have asked how an unfamiliar observer would distinguish a meaningful signal from noise without shared language or prior coordination. The answer consistently points toward frequencies defined by nature itself. The hydrogen line, as a consequence of atomic structure, offers such a definition. It acts as a reference that any observer with sufficient technological capability would independently identify. Importantly, this does not elevate every signal near this frequency to special status. Most detections align perfectly with known hydrogen emissions and reinforce existing models of galactic structure. The value of the frequency lies in how well its normal behavior is understood. That understanding creates a contrast against which anomalies can be measured. Without that contrast, unusual signals would be far more difficult to recognize. This historical and conceptual background influences modern analysis in subtle ways. Analysts are aware that expectations can bias interpretation, so they work carefully to separate the significance of the frequency from the behavior of the signal itself. The frequency alone does not make a detection important, it simply ensures that the baseline is well defined. In this way, the hydrogen line functions as both a scientific tool and a conceptual anchor. It represents the idea that the universe offers certain natural signposts, features rooted in physics that can be recognized anywhere. When signals appear in these regions, they invite closer examination not because of speculation, but because they intersect with one of the most universal markers we know. Another aspect that drew careful attention was the signal's behavior in frequency space. Rather than spreading broadly across the radio spectrum, it appeared confined within a relatively narrow band. This is significant because most natural radio emissions are not so restrained. Astrophysical sources tend to produce signals that are smeared out over a wide range of frequencies due to thermal motion, turbulence, magnetic fields, and relative motion between the source and the observer. These effects act together to blur emissions, softening their edges and giving them gradual transitions rather than sharp limits. In this case, the signal's bandwidth was unexpectedly tight. Its energy was concentrated, not dispersed, and that concentration remained consistent across repeated detections. Narrow bandwidth implies that whatever process produced the signal operated under stable conditions. Random processes, especially those involving hot gas or chaotic magnetic environments, usually inject variability that broadens a signal. Here that variability appeared constrained, suggesting a mechanism with a high degree of coherence. Equally notable were the sharp boundaries of the signal. When plotted, its rise from background noise was abrupt, and its disappearance was just as sudden. There was little evidence of the gradual tapering that typically accompanies natural emissions. In many astrophysical contexts, signals fade as energy dissipates or as emission regions rotate out of view. The clean on-off profile observed here implied a process that starts and stops decisively rather than one that drifts into and out of detectability. These sharp edges are important because they challenge common assumptions about how radio waves are generated in space. Even pulsars, which are among the most regular natural radio sources known, often show complex substructures and frequency-dependent smearing caused by the interstellar medium. A signal with crisp boundaries suggests either an unusually local source with minimal distortion along its path, or a source whose emission mechanism is inherently precise. The combination of narrow bandwidth and sharp edges also reduces the likelihood that the signal is an artifact of interference. Human-made radio transmissions often occupy narrow bands, but they usually carry modulation patterns, harmonics, or sidebands that reveal their origin. In addition, terrestrial interference tends to appear simultaneously across multiple observing stations or frequencies. The signal under analysis did not exhibit these telltale signs, making simple contamination an increasingly weak explanation. From an analytical perspective, these characteristics made the signal easier to isolate, but harder to explain. Its clarity allowed researchers to define its parameters with confidence, yet those same parameters did not align neatly with known categories of natural emission. This tension is a hallmark of scientifically interesting observations. The data are clean, but the interpretation is not. Ladies and gentlemen, when we search the universe, we expect chaos, we expect randomness, we expect noise. But sometimes the universe answers back with something different. While analyzing radio data centered around 1420 MHz, a frequency astronomers know well, something unusual appeared in the signal associated with 3i-G-ATLIS. At first glance, it seemed ordinary, another faint whisper lost in the cosmic background. But as the data unfolded, patterns began to emerge. Patterns that do not behave like natural noise. Noise is messy, it fluctuates unpredictably, it has no memory. But this signal showed structure. What stood out immediately was repetition. Not constant repetition, but precise recurrence, like a pulse, a brief emission followed by silence, then another pulse, spaced with striking regularity. This is why it feels less like static and more like a ping, a deliberate emission, a momentary tap on the vast fabric of space. The significance of 1420 MHz cannot be ignored. This frequency corresponds to the hydrogen line, produced by the most abundant element in the universe. It is a natural cosmic marker, visible across interstellar distances and largely free from interference. For decades, scientists have considered it a logical channel for long-distance communication, precisely because any technologically aware civilization would recognize its importance. That does not mean this signal is artificial, but it does mean it deserves attention. When natural astrophysical sources emit radio waves, they usually leave fingerprints, Doppler smearing from rotation, thermal broadening, chaotic modulation from magnetic turbulence. This signal showed surprisingly clean boundaries. Its bandwidth was narrow, its rise and fall were sharp. It behaved less like a storm and more like a knock. A ping is not a message, It carries no language, no images, no information, only intent. It says something is here. In radar systems, pings are used not to speak, but to locate, to probe, to announce presence. That analogy is difficult to ignore when examining this data. Further analysis ruled out many common explanations. It did not align with known satellite interference. It did not match terrestrial reflection patterns. Its timing did not correspond with known pulsars or fast radio bursts. Each possibility removed made the signal more interesting, not more alarming but more curious. Importantly, curiosity is not belief. Science does not jump to conclusions. It builds them carefully, step by step. Extraordinary claims demand extraordinary evidence, and this is not evidence of intelligence. It is evidence of anomaly, something that behaves differently from expectation. And anomalies are where discovery begins. Throughout history, our understanding of the universe has expanded not because everything made sense, but because something didn't. From the motion of planets to the background glow of the Big Bang, progress came when observations refused to fit our models. This signal, whether it turns out to be an unknown natural phenomenon, a rare interaction of cosmic matter, or something we have yet to imagine, reminds us of an essential truth: the universe is not obligated to be simple. Calling it a ping is not a claim. It is a description, a metaphor for precision, for structure, for intention, like behavior without assuming intention itself. It reflects caution, not certainty. What matters most is not what this signal is, but what it represents. It represents the moment when noise becomes pattern, when randomness becomes question, when silence briefly feels interrupted. And in that moment, we are reminded why we listen at all. Because sometimes when we aim our instruments into the dark and expect nothing in return, the universe surprises us, not with answers, but with the invitation to keep listening. When astronomers and radio scientists point their instruments toward the sky, they do so with the full expectation of encountering randomness. The universe, at radio frequencies especially, is a loud and crowded place. Countless natural processes generate electromagnetic emissions, stars radiate energy as a result of nuclear fusion, planets reflect and scatter signals, clouds of gas glow faintly at characteristic wavelengths, and energetic events such as supernovae and black hole accretion disks inject bursts of radiation into space. On top of this cosmic background, there is the constant hiss of thermal noise produced by the instruments themselves. All of this combines to create a complex, shifting sea of signals that rarely form clean, orderly patterns. In radio astronomy, noise is not a flaw or an error. It is the default state of the universe as we observe it. Random fluctuations in signal strength, frequency, and timing are expected because the sources are numerous, distant, and often chaotic. Even when a signal is strong, it is usually smeared across a range of frequencies or distorted by the motion of its source, the interstellar medium it passes through, and the relative motion of Earth itself. This is why scientists spend so much time filtering, averaging, and modeling their data. The goal is not to find perfect clarity, but to extract meaning from disorder. Most of the time, this process confirms what we already know. A suspected signal dissolves into background interference once analyzed closely. A spike in the data turns out to be local radio pollution, a satellite passing overhead, or a brief instrumental artifact. These outcomes are not disappointments, they are part of the scientific method. By ruling out false positives, researchers refine their techniques and improve their understanding of both the universe and their own tools. Because of this, expectations are deliberately conservative. Astronomers do not begin their analysis hoping to find something extraordinary. Instead, they assume that whatever they detect has a mundane explanation until proven otherwise. This mindset is essential, especially in fields like radio signal analysis, where the temptation to overinterpret patterns can be strong. Human perception is naturally drawn to repetition and structure, even when none truly exist. Science guards against this bias by demanding statistical significance, reproducibility, and consistency with known physical laws. Against this backdrop, the idea that a signal might stand out as anything other than noise is inherently striking. It is not because the universe is usually silent, but because it is usually too noisy. Order is rare, clarity is rare. A signal that does not immediately blend into the background challenges assumptions built from decades of observation. It forces analysts to slow down, to question their filters, their models, and their expectations. Importantly, the rarity of such moments explains why caution dominates the interpretation. Scientists are trained to be skeptical, not because they resist discovery, but because they respect how easily randomness can masquerade as meaning. The history of astronomy is filled with examples where initial excitement faded under closer scrutiny. Each of these cases reinforced a collective discipline. Extraordinary interpretations must wait until ordinary explanations are exhausted. Therefore, when researchers say that they expect noise, they are not expressing pessimism. They are expressing realism. The universe is vast, active, and indifferent to human hopes. Most of what it produces is uncoordinated and impersonal. That is precisely why the careful identification of anything that appears structured, persistent, or patterned becomes so important. Such findings are measured not against excitement, but against a long tradition of cosmic chaos. In this context, recognizing that the search normally yields nothing but noise sets the foundation for understanding why any deviation matters at all. Only by appreciating how overwhelmingly random the cosmic radio environment is can one grasp the significance of encountering something that resists immediate classification. The analysis centered on a very specific region of the radio spectrum, one that astronomers have studied with exceptional care for decades. The frequency of 1420 MHz is not chosen arbitrarily. It corresponds to a natural emission produced by neutral hydrogen atoms, the most abundant element in the universe. When the electron in a hydrogen atom flips its orientation relative to the proton, it emits a photon at this exact frequency. This event is rare for any single atom, but across the immense quantities of hydrogen spread throughout galaxies, the collective effect becomes measurable and profoundly important. Because hydrogen fills the space between stars and galaxies, the 1420 MHz signal acts as a kind of cosmic map. By detecting it, astronomers can trace the structure of spiral arms, measure the rotation of galaxies, and study the distribution of matter far beyond what visible light can reveal. Entire fields of astrophysics are built around observing this single spectral line. It is one of the few frequencies that can travel vast distances through space with relatively little absorption or distortion, making it a reliable messenger from the deep universe. This same reliability is what gives the frequency its broader significance. Unlike many other parts of the radio spectrum, 1420 MHz is quiet in a very specific way. International agreements protect it from most human-made transmissions, recognizing its importance to science. As a result, it is less cluttered by terrestrial interference than neighboring frequencies. For analysts, this means that signals detected here are less likely to be contaminated by everyday human activity and more likely to originate from beyond Earth. Over time, this frequency has also taken on a symbolic role in discussions about cosmic detection. Because hydrogen is universal and its spectral signature is rooted in fundamental physics, any technologically capable civilization studying the universe would almost certainly discover it. That makes 1420 MHz a kind of shared reference point, a frequency that does not depend on culture, language, or biology, but on the basic structure of matter itself. This universality has led scientists to pay particular attention to this band whenever something unexpected appears within it. Focusing analysis on this frequency therefore carries both scientific and philosophical weight. Scientifically, it provides a well-understood baseline. Decades of observation have established what typical hydrogen emissions look like, how wide they are in frequency, how they shift due to motion, and how they vary in intensity across different environments. Any deviation from these expected patterns becomes immediately noticeable. Analysts can compare new data against an enormous archive of prior measurements, increasing confidence in identifying what is normal and what is not. Philosophically, concentrating on the 1420 MHz reflects an assumption about communication across the cosmos that simplicity and universality matter. If something were to be intentionally detectable over interstellar distances, it would likely appear at a frequency that stands out against the background and is naturally meaningful. Even without assuming intention, the human tendency to examine this frequency closely is rooted in its clarity. It is a place in the spectrum where nature itself speaks consistently. In the case of 3i de Lass, centering the analysis on 1420 MHz was not about searching for answers, but about applying the most reliable lens available. By narrowing attention to a frequency with well-known behavior, researchers reduce ambiguity. They can say with greater confidence whether a signal aligns with known hydrogen emissions or whether it departs from them in subtle but important ways. This careful focus does not imply expectation of discovery, it reflects discipline. The more familiar scientists are with a frequency, the more sensitive they become to anomalies within it. When something appears slightly out of place, that recognition comes not from excitement, but from deep familiarity. In this way, the choice to analyze the 1420 MHz band becomes a foundation for careful, responsible interpretation rather than speculation. The signal linked to 3i de Lass did not immediately announce itself as unusual. In its earliest form, it blended into the surrounding data much like countless other detections recorded every day by radio instruments. This is an important detail because truly extraordinary findings in science rarely appear dramatic at first glance. They often begin as subtle irregularities, nearly indistinguishable from background activity, and only reveal their significance after patient and methodical examination. At the initial stage of analysis, the signal behaved in ways that were entirely familiar. Its strength fell within expected ranges, and its presence did not trigger any automated alerts designed to flag extreme or obviously artificial events. To an untrained eye, it would have looked like just another faint fluctuation, the kind that fills radio datasets and is usually filtered out without a second thought. This apparent normality is precisely why it passed through early processing without special attention. The shift occurred when analysts began applying deeper scrutiny. Instead of looking at the signal as a single moment in time, they examined how it behaved across extended intervals. This temporal perspective revealed that the signal was not isolated. It reappeared, not continuously, but intermittently, and in a manner that resisted easy explanation. The recurrence was subtle enough to avoid immediate detection, yet consistent enough to raise questions once it was noticed. As the data were reprocessed with finer resolution, additional details emerged. The frequency of the signal remained remarkably stable from one appearance to the next. Natural radio sources often drift due to relative motion, gravitational influences, or changes in their physical environment. Even small variations can smear a signal across the spectrum. In this case, however, the frequency alignment was unusually precise, suggesting a source that was either highly stable or governed by a mechanism not commonly observed in similar contexts. Further analysis focused on the signal's shape. Noise typically produces irregular, jagged profiles that differ each time they appear. This signal, by contrast, showed a repeating structure. Its rise and fall followed a similar pattern on multiple occasions, as though the same event were being replayed. This kind of consistency does not automatically imply anything extraordinary, but it does narrow the range of plausible explanations. At this point, analysts began to question their assumptions. Was the signal an artifact of the instrumentation? Could it be the result of a processing error, a calibration issue, or a subtle form of interference? These possibilities were explored systematically. Independent datasets were consulted, and cross-checks were performed to ensure that the pattern was not being introduced artificially by the analysis pipeline itself. Each check strengthened the conclusion that the signal was genuinely present in the raw data. What made this stage particularly important was the contrast between expectation and observation. The expectation was that further scrutiny would dissolve the signal into randomness, revealing it as nothing more than coincidental alignment within noise. Instead, the opposite happened. The more closely the signal was examined, the more its internal coherence became apparent. This is a critical moment in any scientific investigation when confidence begins to shift, not toward a conclusion, but toward the recognition that something deserves sustained attention. Despite this, restraint remained essential. An unusual signal is not the same as an unexplained one, and an unexplained signal is not evidence of anything beyond natural phenomena. The goal of deeper analysis was not to assign meaning, but to characterize behavior. By documenting how the signal differed from typical background noise, researchers created a foundation for future investigation, whether that ultimately leads to a novel natural explanation or a refinement of existing models. The journey from ordinary to interesting was gradual, built on layers of verification rather than sudden revelation. That progression is what gives the signal its significance. It did not demand attention through intensity or spectacle, but earned it through persistence and consistency. One of the most striking features of the signal was not its strength or its frequency, but its timing. As the data were examined over longer durations, a pattern began to emerge that set it apart from typical background activity. The signal did not appear once and vanish forever, nor did it fluctuate chaotically as noise usually does. Instead, it returned, again and again, each appearance separated by intervals that were not random, but measured and consistent within a narrow margin. Repetition alone is not unusual in astronomy. Many natural sources produce recurring signals. Pulsars rotate and emit beams at regular intervals, orbiting systems create periodic variations, and even instrumental effects can introduce repeated artifacts. What made this case different was the character of the repetition. The timing was neither perfectly clock-like nor erratic. It occupied an intermediate space that resisted easy classification, suggesting a process governed by stability, but not simple rotation or orbital motion. The precision of the timing was particularly notable. When the intervals between signal appearances were plotted and compared, they clustered tightly rather than spreading out. Random noise, by definition, lacks such consistency. Even when noise produces apparent spikes, the spacing between them varies unpredictably. Here the spacing showed memory, as if the system producing the signal followed a rule. That rule was not immediately obvious, but its presence was difficult to dismiss. Equally important was what the signal did not do. It did not drift progressively closer together or farther apart in time, as might be expected from a decaying orbit or an unstable emission process. Nor did it synchronize with known periodic sources in the sky. This ruled out a number of common astrophysical explanations early in the analysis. Each eliminated possibility sharpened the focus on the timing itself as the key feature demanding explanation.